So as Dr. Avery said, today I'm going to be talking to you about automatic construction, maintenance, and optimization of dynamic agent organizations. So we as humans, when we have a common goal and we get together to try and achieve that goal, we often have this innate knack for organizing ourselves into structures that better enable our coordination. For example, in business or in corporations, when you get to a certain size, it makes sense for people to take on roles and to organize themselves into some type of hierarchy. And as humans, we're very good at adapting when, for example, new people join the collective, and inevitably when people leave the collective. And we're able to adapt as these organizational problems change. And when we as humans design computer systems, we tend to design them similarly. For example, when we make a Google search query, there isn't some supercomputer sitting in Mountain View, California that is processing all of the millions of requests per hour. There's a whole cluster of different computers that each take on certain different roles that balance the load of the computation. And this may be a little bit of a stretch, but I argue that nature in and of itself sort of self-organizes. There's this folkloric experiment in computer science that if you take a piece of sheet glass and you put some pegs on the glass in random locations and then sandwich that between another piece of glass, and you dip that contraption into a vat of soapy water, then when you pull it out, the soap bubbles will be attracted to those pegs, and they will actually form a structure between connecting all of the pegs. And if you were to measure the lengths of those soap film structures, it would actually be the minimum length structure that you could possibly construct between those pegs. And the reason why this is an interesting problem is because this is what's called the Euclidean Steiner network problem. And it was actually one of Karp's original NP-complete problems. So there are some interesting implications here if you're interested in digital physics or new kinds of science as to what this means for the P equals NP problem, but that's sort of irrelevant. The thing that interests me about this is that if we were to consider each of these pegs as agents, as autonomous software agents, then this structure we can think of as, in effect, a minimum cost way for each of those agents to communicate with each other. So building these types of structures can help these agents in whatever type of coordination they may have to execute. So the ultimate problem that I'm trying to address with this dissertation is, given a notion of the way in which a group of software agents need to interact, what is the best organizational structure for that system that might expedite the process of coordination while maintaining a certain operating point? So each of the agents has some local view of the world with only local information. For example, agent 1 may know that it needs to interact with agent 2. Agent 3 may know that it needs to interact with agents 4, 7, and 12. But no one agent necessarily has a global view of the world. So ultimately what we want is some type of process by which all of the agents can, in a distributed manner, coordinate with each other to try and figure out some structure that better enables their coordination. For example, a Steiner network, or maybe some other type of organizational structure. So what this dissertation is doing is it's filling in a small portion of this box by providing parallel and distributed algorithms for doing just that. So some of the contributions of the work include identifying a set of connectivity problems, which are called constraint forest problems, that capture many of these multi-agent organization problems. So we can have these sort of high-level multi-agent organization problems And I'm arguing that a large portion of them actually map to connectivity problems. We give parallel and distributed algorithms for solving these problems, and we have good bounds on their runtime and optimality. And we have a tangential result that for combinatorial optimization problems on finite structures, any randomly chosen feasible solution in many cases is with high probability a constant factor of optimal. I'm going to give some examples of how this framework for solving these distributed constrained forest problems can be applied to some real-world domains, including art gallery problems, which have to do with sensor networks and robot teams, facility location, etc. And finally, the ultimate goal of what we're trying to do here is provide algorithms that can solve dynamically changing problems. So I give some extensions to this framework to allow for dynamism. So the outline for this talk roughly follows these contributions. First, I'm going to introduce the algorithm. Then I'm going to talk about the combinatorial statistics result for finite structures. Then I'm going to give some examples of how we can apply the framework, followed by the dynamic extensions. So first, a little bit of background as a refresher from my proposal. So some of the things that I argued there. Well, first, by this point, I hope that you would agree that distributed multi-agent organization is a hard problem, yet a solution to it would be useful. Measuring the performance of distributed systems is also hard. But ultimately, one of the things I argued in my proposal was that in most cases, what we really want is at most a linear number of messaging rounds for these algorithms to find these organizational structures. Approximation algorithms are often useful and sometimes necessary. And the primal dual schema is a very powerful tool for approximation. And what I concluded in my proposal was that the primal dual schema seems like it is distributable. And it turns out that it is. So the idea behind how we are going to solve these problems is that, as I mentioned before, we are going to represent the agent's interaction constraints as a graph, and then solve the connectivity problem on the graph using a form of search. So as a quick overview of search, in classical search, you have a start state and a goal state. And from the start state, we expand the successors from that state and add them as open nodes to what's called the fringe. Then we look at the fringe, we remove one of the nodes from the fringe and do the same thing, we expand it. And we remove another node from the fringe, and this continues until eventually, perhaps, we find a path to the goal. Now, depending on how we choose to prioritize which nodes we pull from the fringe, that defines what type of search it is. If we represent the fringe as a stack, we get deep depth first search, and so on. Now, almost 40 years ago, this notion of bidirectional search became popularized. And here, if we know what the goal state is, we can perform two simultaneous searches, each emanating from one of these terminals. And at any point when their fringes overlap, then we have immediately identified a path between them. Now, if we modify the goal test function, which is the function that tells us when to terminate our search, and we don't just terminate when we get that overlap, but we terminate when both searches expand the same node. And we use two searches that have guaranteed optimality, then this path that is discovered is guaranteed to also be optimal. And if we are able to perform these searches efficiently in parallel, then there's the potential to get a speed up from parallelism. Now the question is, what happens if there is a third terminal that also wants to be connected to everyone else? For example, in the Steiner network problem, there were 3 pegs that were connected by SOAP. How can all three of these guys find some minimum weight structure in the search space that connects all three of them. So one idea might be to do multidirectional graph search. And if we think about the way the soap bubbles may be behaving, is that they are trying to find the state of least potential energy. So as they disperse, they are attracted to each other and eventually converge to a minimum, or perhaps minimum, structure. And maybe we can create some type of search that performs in the same way. But the challenges to this are, how do we prevent cycles? We're trying to find tree structures here, forests, yet each of these individual searches may create a cycle. How do we ensure that if a solution exists, we will actually find it? And how can we say anything about optimality? Perhaps we may just be doing local optimization and finding a local minimum. Well, it turns out that we can solve all of those challenges. And this is the general algorithm that, on which this distributed multi-agent organization framework is based. And I call it the generalized distributed constraint forest algorithm for multidirectional graph search. Now I realize this is a little bit of an eye chart, so I'm going to break it down for you. This is really basically like classical search. Here, we are just initializing the fringe and initializing all of the, for example, the path cost function is initialized to 0, just like in regular graph search. Here, we are checking for the goal test function. As long as each of our structures is not connected to each other, then we keep on searching. Here, we are expanding a node from the fringe of minimal potential according to this special potential function. That's how we're prioritizing our fringe. And this, we will see in a little bit, is what is going to provide the quality guarantees for the algorithm. Here, we are updating the path cost for all of the nodes in the fringe. And here we are expanding successor states. Basically like regular search. The big difference here is that this potential function is acting essentially like a gradient, helping each of the, or a heuristic, helping each of the independent searches find each other. And if this potential function has certain properties, well-defined properties, which I will show, then we can ensure bounded optimality of the solution. And here, essentially the path costs are equivalent to the dual variables in the dual optimization problem. Here, we're solving the primal. The path costs are the dual variables which we are pushing up by updating the path costs, and that identifies which primal variable we should identify, or in other words, which search node we should identify to pull from the fringe. And here's where we update those dual variables. So some properties of this algorithm. First, we have polynomial local runtime and memory usage. We also have a proof that selecting nodes in parallel will not induce a cycle in the constraint forest. The assumption that makes that happen is that every vertex has a unique identifier, which is, we think, a reasonable assumption for most problems. The algorithm is correct and complete. Now, we have a proof that if there exists a metric space such that all of the edge weights fall into this metric space, basically if all of the edge weights are relatively close to each other, if the variance of their distribution is relatively low, then the solution this algorithm finds is guaranteed to be 2 optimal. Alternatively, if we can't ensure that requirement, then there are other circumstances by which we can ensure 2 optimality. For example, if we can bound the number of edges that will be added to the network later on as the algorithm executes. So in terms of, now recall that ultimately what we're trying to minimize here is the, one of the many things we're trying to minimize is the longest causal chain of messages, or in other words, messaging rounds that is required for the algorithm to quiesce or to terminate. And here, this is a function of what type of communications network the algorithm is communicating over, if it is being run distributedly. If all of the agents can communicate with each other in a constant number of messaging rounds, for example, if you have like a star topology, or if they're all connected to the same network router, then we have a logarithmic number of messaging rounds.
What was the definition of alpha?
Oh, I'm sorry. Alpha is, so in terms of the Steiner network problem, alpha is the number of terminals, basically the number of pegs there are in the graph. And n is the total number of nodes in the graph. So we achieve a logarithmic number of messaging rounds. And this is actually, from a recent result from Elkin, this achieves the lower bound on the time approximation trade-off. But even in the worst case, in other words, if all agents can't necessarily communicate with each other peer-to-peer directly in one messaging hop, essentially, we either have polylogarithmic runtime or polynomial runtime, depending on the problem domain. But for both of these cases, the convergence to this upper bound is sublinear. So yes, in this worst case, it is linear. I'm sorry, it is worse than linear, but the convergence to that upper bound is sublinear. Now, we also have a procedure for trading off computation time and the approximation bound. If we have an upper bound on essentially the heaviest edge, or the costliest edge in the network, a finite upper bound, then we can get an epsilon optimal solution. We can get arbitrary optimality at the expense of additional messaging rounds, at the expense of additional runtime. So for example, if we want epsilon to be 2, to ensure a 2 optimal solution requires this many messaging rounds. And if this upper bound on the heaviest edge satisfies this inequality, then we will only need polylogarithmic additional rounds. So in this case, if we can ensure, if we have this upper bound, then in many cases we can solve the entire problem in polylogarithmic runtime. So this means that we have a fully polynomial time approximation. So I've given you sort of a high-level overview of how the algorithm works and what its properties are. So now I'm going to talk to you about this, in some ways, independent result, or complementary result on combinatorial structures and approximating solutions to them. So consider a problem on some finite structure. Here I have a random lattice, but it could really be any finite structure, graph, or anything. Now, imagine that we're trying to solve some combinatorial optimization problem here. We're trying to find some subset of the edges that satisfies a certain property. Okay, so here I've weighted all of the edges. So here I sorted all of the edge weights. Okay? Now, in the absolute worst case, let's say we have some algorithm that finds a feasible solution to this. In the absolute worst case, that algorithm is going to choose the heaviest edges, right? That may not even correspond to a feasible solution, but that is the worst case. If you sum the weights of those edges, it can't be worse. So let's say that we know our algorithm is going to find a solution that has at most L edges. Then the sum of those L heaviest edges is an upper bound on how bad that algorithm is going to do. Now let's say, also in the worst case, our algorithm chose the heaviest edges, but the optimal solution consists of the lightest edges. Now if we know that the optimal solution has at least M edges, then we know that the approximation bound of our algorithm is bounded above by the sum of these L heaviest edges divided by the sum of the M lightest edges. That's the absolute worst case. Thereby, it's an upper bound on how bad our algorithm is approximating the solution. But a reasonable observation to make is that we don't always know all of the finite edge weights for a given search space. We may not even know all of the edges. But what we may know is a probability distribution over the edge weights. So taking that ratio of finite edges and then converting it to probability distributions results in this what's called a ratio distribution over the sum of the truncated order statistics of the distribution of edge weights. Okay? So then the expected value of this z distribution is an upper bound on the expected value of the constant, of the true constant of approximation of your algorithm, even though we haven't fixed what algorithm it is, and so on. And that's ultimately what we're looking for. We're looking for some upper bound on the expected constant of approximation. The problem is, this is an open problem. There is no closed form for that z distribution. And the reason why there is no closed form is that the sum of order statistics corresponds to a linear number of nested integrals. And there's no known closed form for this. But we can create a recurrence for it and then use numerical methods to evaluate it for specific distributions. So for example here, I have a plot for the cumulative distribution function for the distribution of the sum of the L largest order statistics for the standard uniform distribution. Now the thing to take away here is that even for large values of L, this gradient, the gradient of these these functions approaches 1 at very steeply, which means that the variance of the z distribution is relatively low. And to summarize, what this eventually leads to is that for continuous uniform distributions, that quotient is a relatively unbiased estimation of the true expected value of z. And furthermore, for uniform, normal, and exponential distributions, we have the expected value of this distribution. It actually turns out to be L over m. And by the central limit theorem, for large enough L and m, this holds in general. So this was really surprising to me, because it has some really interesting implications. For example, if we know the size of the optimal solution is bounded below by m, then any randomly chosen solution of size, feasible solution of size at most L will on average be L over m times optimal. So for the Steiner network problem, we know we have bounds on L and m because if there are alpha terminals in the Steiner network problem, then we know that the optimal solution must have at least alpha over 2 edges. And any feasible solution is going to have at most n minus 1 edges. Therefore, any randomly chosen feasible solution to this problem will be on average that many times optimal. And if every vertex is a terminal, then feasible solutions are with high probability 2 optimal. This has even stronger implications for the minimum spanning tree problem because the bounds on L and M are the same. that means that any randomly chosen feasible solution to the minimum spanning tree problem will with high probability be optimal. And this is regardless of which algorithm you use. If you can enumerate all possible minimum spanning tree feasible solutions and choose a feasible one at random, on average, it's going to be optimal. So now I'm going to talk a little bit about solving, or how we can apply this framework to some real-world problems and how it actually performs on average. So we performed some empirical analysis on Steiner network problems. We generated a few hundred random graphs using the Ardèche-Régnier model. And here we can see that the algorithm performs worse for sparse graphs. Here, the normalized cost, a cost of 0 means the optimal solution was found. A cost of 1 means the worst possible solution is found. So here we were just trying to see what are the worst cases in terms of edge density. So I fixed edge density at 0.1 and reran the experiments just as sort of a worst case scenario and recorded the number of messages. Because of course we do have a bounded number of messaging rounds, but we'd like to see on average how many rounds it's required. Now recall that these are 200. There are 200 agents communicating with each other, and this quickly converges to only around 5 messaging rounds for this algorithm to terminate. And we also recorded the approximation bound. Now we do have the fixed upper bound of 2. We're never going to find a solution that's worse than 2 optimal, but on average we can see we're actually doing much better than that for these types of random graphs, with an average of about 1.2 to 1.3 mean approximation. Yes. So this is, in a sense, the worst case. So going back to the algorithm, so far we've just sort of been using the Steiner network problem as a running example. But it turns out that if we change this goal test function, then we can solve a number of other interesting problems. And furthermore, if this goal test function is a special type of well-behaved function called a proper function, then we retain all of the same theoretical runtime and optimality bounds that we had for the Steiner network problem. So to give you some examples of what types of problems can be encoded using proper functions, we can encode the perfect matching, the minimum perfect matching problem. This is the the goal test function for that. T-join, minimum spanning tree. Of course, we know Steiner tree. The point-to-point connection problem, partitioning, location design, and vehicle routing, and so on. Even the traveling salesman problem. There's a large family of problems that also correspond to some real-world domains. Specifically, I'd like to talk about a sensor network and robot teaming problem. So imagine a group of mobile robots, each equipped with a wireless access point. The objective of the robots is to maximally cover an area with their wireless networks. But in order to save power, they need to choose a maximum subset of the robots that can lower their transmit power while still retaining coverage. And there's also an equivalent sensor network problem, which I talked about in the dissertation. But ultimately, this problem, I argue, can be encoded as a type of art gallery problem. So the classic art gallery problem is given some polygon, we need to find, so we create what's called a visibility graph, which is essentially a graph representing which vertices can be seen by which other ones. And we want to find some minimum set of guard locations that are sufficient to observe the entire interior of the polygon. And there are a number of different variants on this problem. For example, we can have guards in the interior of the polygon. We can have treasures of different value that we need to guard. We can have a non-uniform cost for stationing guards in different locations, and so on. But a large many of these variants are in fact NP complete, including the one that we are investigating. So now I'd like to motivate the fact that we can actually solve this art gallery problem or approximate it as if it were a connectivity problem. So here, this is the visibility graph for the polygon. And the first step is to augment each vertex with a special guard vertex, which I've drawn in red. We weight those new edges with the cost of adding a guard at that location. Here I've just added a cost of 1. And then we weight all of the other edges according to the quality, for example, of that line of sight. Here I just give them all an equal cost of 0. Then the connectivity problem is to find an acyclic subgraph such that every regular vertex or guard location is connected to a guard vertex by a path of length, or in this case weight, less than or equal to 2. And that subgraph's weight is minimized. So to give you an example here, this is a solution to the connectivity problem. This, you can see it very well. That is the solution to the connectivity problem. And then every black vertex that is adjacent to its associated guard vertex in the subgraph becomes a guard. And we have our solution. So the way we can use multidirectional graph search to solve this is, initially, each of the possible locations has an agent at it. And each agent performs a multidirectional graph search emanating from its location. Here, I've drawn unguarded vertices with a white dot in the middle. So during the first round, each search chooses essentially at random a successor node from its fringe. And they get added to the overlay network, or the subgraph. And now every agent that is in the same connected component, they merge their searches. So then all of their independent searches act as a single cohesive search. They merge their fringes. So then during the next round, this search has chosen to expand this edge from its fringe. This search has chosen to add this one, and this edge was actually mutually chosen. So now, essentially, all of the agents are in the same search. And one by one, we expand additional nodes. Here, since an edge was added connecting a guard vertex, the adjacent node becomes a guard. And we keep on going until the goal test function has been satisfied, or in other words, when all of the vertices are guarded. And we have a solution. Now, this solution, of course, is not the optimal solution because we saw that there is a solution with 2 guards, but it is 1.5 times optimal. So we ran this a number of times without ensuring to optimality. We didn't use the edge distribution that ensured that, but we can see that even without adding those additional messaging rounds or encoding the edges using the special metric space, we still get a rather constant average constant of approximation invariant of the number of agents. So now I'm going to talk about what this whole thing has been leading to, is the ability to solve these problems as the problem is actually changing. And in a sense, this is the distributed counterpart to online algorithms in the sequential model. And the approach for doing that is to provide algorithmic extensions that allow for the addition, update, and removal events of vertices and edges, via a super stabilizing algorithm and adding a form of backtracking to the search. So some results from this dynamic extension are that, first, in certain well-defined cases, after a change happens to the problem, the algorithm can be continued on off from where it left, and without changing anything, and we're still guaranteed to produce a solution that has the same optimality bounds as before. Now, the specific case for that to happen is we need to know that all of the weights of the new vertex's incident edges are greater than or equal to the slack of all of their neighboring vertices fringe nodes, which is a mouthful, but it's relatively easy to test for this property. We can do that in a constant number of messaging rounds. So we can test if this property holds. Now, if it doesn't hold, meaning that if we did do this, then we weren't necessarily guaranteed to have the same optimality bounds, then what we can do is we can backtrack the search to the most recent round where those properties did hold. And we're always guaranteed to have those properties at round 0. So in the worst case, we're just going to backtrack all the way back to where we started in round 0. But since the number of rounds is bounded above by n, then we're only going to, in the worst case, we're only going to incur a linear number of backtracks. But in the average case, or one would hope that in many instances, we're actually going to find a state much earlier than having to backtrack all the way back to the beginning. Also, the additional bookkeeping required for this backtracking procedure only increases memory and computation polynomially. Now, another reasonable question to ask is, what if we have a problem that cannot be represented using proper functions? So it's too expressive, or it doesn't, the goal test function is not a proper function. So an example of this that is actually what got me interested in these types of multi-agent organization problems in the first place is the pseudo-tree construction problem. So recall that the pseudo-tree construction, recall from my proposal if you were there, that the pseudo-tree construction problem is to find minimum depth rooted tree such that every pair of neighbors in the interaction graph is either an ancestor or descendant of one another in the pseudo-tree. And this has important implications for especially distributed constraint reasoning, because many of the algorithms that have been developed in that field require some method of generating efficient pseudo-trees. And so far, there are only a few different approaches, one of which is distributed depth first search, but I'll get to that in a minute. Now, these types of problems are not representable using proper functions because, one, pseudo-trees are rooted, which violates a sort of symmetry property of proper functions. And we need to keep a global invariant over the ancestor and descendant relationships. And it turns out that proper functions at least don't appear to be expressive enough to solve this. So to address this problem, we did another algorithmic extension called MOBED that addresses these problems. So MOBED, like the previous distributed dynamic extension, allows for agent removal, merging of hierarchies, and initially generating hierarchies, and so on. And it has a number of advantages over its depth-first search alternative. It has the same asymptotic runtime for a single agent addition or a single perturbation to the network. However, the runtime can be constant if the number of interaction graph neighbors is also constant. And most importantly, edit distance is bounded by 2. And what I mean by edit distance is if we have an existing optimized structure and a change occurs to it, we don't want the new structure that is the new optimal after the change to be that much different than what the previous one was. So we want the distance from the delta between the previous state to the new state to be relatively small. And for MOBAD, it's bounded by a constant, a relatively small constant. And we validate these results empirically in a comparison to depth first search. And we show that for Erdős-Rényi graphs, we have almost a 300% improvement over depth first search. And MOBAD for Garabasi-Albert small world graphs almost always performs better in terms of edit distance than DFS. So in conclusion, we have identified a large family of multi-agent organization problems, collectively called constraint forest problems, that can be solved efficiently in a distributed manner, or also in a parallel manner. We have generalized this distributed constrained multidirectional graph search algorithm based on the primable schema. And as I mentioned, we have a parallel version of this algorithm too. Now, most importantly, we can ensure epsilon optimality at the expense of additional communication errors, which means that this is a fully polynomial time approximation method. And even if we cannot ensure the conditions that allow for the theoretical bound of 2 optimality to hold, we have a probabilistic argument that for any finite combinatorial optimization problems, any feasible solution is likely to be a constant factor of optimal. So we gave a number of examples of how this algorithm can be, this framework can be applied to real-world domains. In the dissertation, we also give some other examples, including the location design and vehicle routing problem. And we've given some empirical analysis, or empirical results, for its average case performance. And interestingly, for the art gallery problem, the decision versions of many art gallery variants are APX hard. However, whether or not they're in APX is an open problem. But by identifying this class of art gallery problems that are amenable to 2 approximation using this distributed algorithm, which can also be run sequentially, we have discovered that this class of problems is also in APX for this subset of the art gallery problems, and thereby it's APX complete. So we've given dynamic extensions to the algorithm that allow for changes to the problem. And also, we've given another dynamic extension called MOBAD for a specific type of problem that is too expressive to be captured by proper functions. Now, in the future, there's still a lot of work to be done in generalizing these techniques, and to better balance the trade-off between trust, edit distance, privacy, and maybe maintaining other invariants over the topology that aren't necessarily captured by proper functions, and maybe generalizing this to other types of well-spaced functions, or, I'm sorry, to other well-behaved functions. And it's still an open question as to whether the 2 approximation result can be further generalized such that to relax the types of requirements that were needed for our current guarantees to hold. But ultimately, we believe that algorithms of this type are useful in creating distributed algorithms for multi-agent organization. Now, the vision here is that one day we may be able to, well, first solve the inverse problem. So given a structure, an organizational structure, given a Steiner tree, is it possible to figure out what the interaction constraints between the agents were that defined it, essentially? And what if we only have a predictive model of the communication constraints between agents? To what extent is it possible to construct an agent organization or social hierarchy that better enables coordination? And there's been a lot of work in social modeling on problems like these. And there's a question of to what extent that body of research is applicable to software agent organizations. And how do we allow for adversarial agents? And borrowing from the social research, in some organizational topologies, certain agents will have more power or social influence. Can we discuss or even quantize that? And given a communications protocol, is it possible to place an a priori upper bound on the amount of social influence a single individual may have? And to what extent can the maximum social influence of a single individual be minimized solely by modifying the communications network and or manually defining the social network? So with that, I'd like to thank lots of people who made this possible. I probably forgot a lot of people on there too, but more than that, I'd like to thank you and offer some time for questions.